Good morning everyone. This is Indrani, working as assistant professor in Aeronautical Engineering College. Today we are going to discuss on the low pass filters. Okay, so first let us see what is the filters, and we can see the various type of filters. Okay, so first what is the purpose of the filters? The purpose of the filter is a frequency selective circuit. The filter is a frequency selective circuit. So frequency selective circuit means what it makes here. So it will allow certain band of the frequencies, and it does not attenuate the signals which are undesired frequency components. So if you want to allow certain ranges of the frequency, and if you want to attenuate, means if you don't want to allow set of the frequencies, then I need to go for the filters. So these filters are mainly the frequency selective circuits. For which frequency it is selecting, that will pass those signals within that frequency, and it will attenuate remaining all the frequency components. So basically filters are two types. One is a analog filter and another one is a digital filter. And what are the analog filters are there? The analog filters are further classified into two types. One is the analog filter and another one is a active filter, and another one is a passive filters. So the active filters and passive filters both will come under the analog filters. So what are the passive filters? Generally till now in many network theory and so many subjects we have seen the passive filters. What are the passive filters? Passive filters consist of the passive components, that is like a resistor, inductor and the capacitor. So if the resistor, inductor and the capacitor is present with respect to the filters, then those are the passive filters. And then what about the active filters? Active filters consist of the active components along with the passive components. So here what are the active components? Active components are here transistors, diodes and operational amplifier. These will be present. Along with that we are using the passive components. So what are the active filters is that? The active filters is the connection between the active elements and passive elements. This makes the corresponding filter section of the active filters. So first let us see, today we are going to discuss regarding the active filters. In these active filters we are seeing the active filters by using the operational amplifier. So first let us see what is the classification of the corresponding active filters. So under the active filters, here first mainly, before going to the active filters, first mainly what is the purpose of the active filters? So the active filters are mainly used to minimize the effect of the loading on the frequency characteristics of the filters. That is the first thing. Second thing is the filters are used for the communication, signal processing. For these type of electronic applications, we are using the corresponding filters. And at the same time, suppose if I want to suppress a noise and if I want to reduce the noise at the low frequency or high frequency, right, and at the same time if I want to eliminate the noise for a set of band of frequencies I want to eliminate, then at that time I can use the filters will be used here. Now what are the different types of the filters? What are different types of filters is, first it will come under the low pass filter. What is a low pass filter? Low pass filter means it allows only the low frequency signals up to the break point, up to the cutoff frequency FH, and later beyond the corresponding cutoff frequency it will suppress the passes of the corresponding signals. So here if you observe this response here, so below this cutoff frequency FH, this FH is called as a higher cutoff frequency. Below this higher cutoff frequency it will pass the signals which is on the frequency, and beyond this frequency it does not allow the corresponding passes of the signals. So this is called as this is a low pass filter ideal responses. This is the pass band and this is the stop band. And if you observe the response graph here, the frequency is taken as the x-axis, and the gain is nothing but the output voltage by input voltage. Modulus of output voltage by input voltage is taken as a y-axis. So this is the ideal characteristics of the low pass filter. But practically speaking, we cannot get the ideal response is not at all equal to practical. This type of sharp dropping the corresponding gain cannot be present. Slowly the gain decreases slowly along with the corresponding frequency component. So that's why here this is the practical response of the corresponding practical response of the low pass filter. And here also this FH is a higher cutoff frequency. Beyond the higher cutoff frequency, when the gain is coming to 0, beyond this higher this frequency, this is a stop band. Below this one, this is a pass band. And whatever this band, there is a transition is there from the pass band to stop band. This range of frequencies are called as a transition band of frequencies. Next, high pass filter. High pass filter means it allows only frequencies of certain frequencies beyond the corresponding cutoff frequency. So beyond this cutoff frequency, which is the lower cutoff frequency, it will allow the passes of the signals. So that's why we are calling this is a pass band, and below this cutoff frequency, this is the stop band. This is a stop band and this is a pass band. And what are the ideal response is there? Ideal response, I am getting a sharp at the cutoff frequency, the gain value is changing from the frequency 0 to FL, sharply it is going. But if you are taking the practical practical high pass filter, in the practical high pass filter, the gain value is changing as the frequency component is increasing. The gain value is changing from 0 dB to the maximum gain we are getting here. So below this cutoff frequency, this lower cutoff frequency, this is a stop band. Beyond this lower cutoff frequency, it is the pass band. The transition band of frequency from stop band to pass band is called as a transition band. Okay. So next, coming for the band pass filter. Band pass filter means it will allow the certain band of the frequencies itself. Certain band of the frequencies means, sorry for this response here. Yeah. So the band pass filter is having the response curve will be like this. What is this response curve here? So whatever this response curve is there, this is the FL and this is the FH, and here this is the stop band. This is the stop band. So it will allow the passage of the signals from this lower cutoff frequency to higher cutoff frequency only. It will allow the passage of the signals, and beyond this lower cutoff frequency and higher cutoff frequency, it does not allow the corresponding passage of the signals. So this is a stop band. This is the ideal practical response, and this is the ideal response of the corresponding band pass filter. This is the band pass filter response looks like this. Okay, so here what are the band pass filter is there? Band pass filter is a combination of high pass filter as well as a low pass filter. It is allowing only specified ranges of the frequencies will be passed. So for this one, what I need to find here? I need to find what is the bandwidth. What is the bandwidth here? The bandwidth is the difference between the higher cutoff frequency and the lower cutoff frequency. So the difference between FH minus FL is the bandwidth of the corresponding amplifier. Okay. Next, band reject filter. Band reject filter means this is doing the inverse operation of the corresponding band pass filter. So inverse operation of band pass filter means only in between certain ranges of frequencies only. It does not allow the passes of the signals, and below this frequency and beyond this frequency, it will allow the corresponding passes of the signals. So whatever this band is there, this band is nothing but it is a stop band. This is a stop band, and below this, beyond this and below this frequency, this is the pass band. So here also this is the pass band here, and this is the pass band, and in between this is the stop band. So if I find bandwidth the difference FH minus FL, then I can identify that what is the stop band frequency I can identify. So if I calculate what is the separate value of FH and FL, below FL and beyond FH, it will allow the passes of the signals. And coming for the first, so this is the with respect to low pass filter, high pass filter, band pass filter and band reject filter, we have seen what are the various responses of the corresponding filters we have seen. Now the next thing is, let us go for the first order low pass filter. First order low pass filter. So here this is a first order low pass filter. So why you are calling this one the first order means, first order means based on number of these RC sections we are taking, we will call this is the order of the filter. Suppose if I am taking the single RC section is there, then that is called as a first order filter. So in addition to that, if I am taking one more RC section, then that is called as a second order filter. Based on the required response, required frequency response here, we can increase the order of the filter to get the accurate output voltage value, accurate frequency versus the gain graph. For best filtering operations, I need to increase the order of the filter, means I need to increase number of RC sections, I need to increase. So here, now first, according to the operation wise, what is the operation here? So here, if you observe here, this is the non-inverting amplifier. For this non-inverting amplifier, we are giving the input for the non-inverting terminal, and whatever the inverting terminal is there, inverting terminal has been short circuited to ground. And here we are giving the input for the non-inverting terminal of op-amp. And whatever this RC is given is there for non-inverting terminal. And coming for the inverting terminal, we are giving the feedback type of connection. The feedback type of connection is a negative feedback has been given here. Okay. Now, here what is the function of this resistor and this capacitor? Now, here if you observe this resistor and the capacitor here, your capacitance, the working function of the capacitance changes with the frequency component. Why? Here, whatever the reactance of the capacitance is there, the reactance of the capacitance is represented as Xc equal to 1 by 2 pi F into C. Okay. So, when the frequency value is low, when the frequency value is very low here, then whatever the reactance of the capacitance is there, the reactance of the capacitance is high reactance will be there. When there is a high reactance, what is the function of your capacitor? Your capacitor acts as a open circuit. The capacitor acts as a open circuit. Okay, because of the high reactance, the capacitor acts as a open circuit. Just imagine there is some open circuit is there at the low frequency. At that time, what will happen? If you see this circuit, without this capacitor, then how the circuit is looking? The circuit is looking like non-inverting amplifier. So for the non-inverting amplifier, what is the output voltage of the non-inverting amplifier? The non-inverting amplifier output voltage is 1 plus RF by RI. The non-inverting amplifier output voltage is 1 plus RF by RI. Okay. So next, as the frequency value is increasing, when the frequency value is increasing, the reactance of the capacitance will be slowly decreases. When the reactance of the capacitance slowly decreases, your capacitor acts as a short circuit. When the capacitor acts as a short circuit, then certain amount of voltage will appear across this capacitor. Now, based on that, so when the capacitor is acting as a short circuit, let us see what is the expression for the output voltage. Okay, so when the frequency value is low value, input signal frequency is low, at that time your capacitor is acting as a open circuit because of the reactance of the capacitance. But when the frequency value is a high value, the reactance of the capacitance value is low, at that time the capacitor acts as a short circuit. So now let us see what is the gain expression. Okay, so this is whatever I have explained, it has been given here. Okay, so yeah, we at a low frequency, the capacitor appears as an open circuit and it is acting as a, at the time, the gain of the non-inverting amplifier will be like this. Now, coming for the high frequency, the capacitor reactance decreases. So, slowly, the voltage gain value slowly decreases from the original value of 1 plus RF by RI. So, now, if I calculate what is the voltage at this node? Voltage at this node V1 equal to, why I need to find voltage V1 here? Because I need to find what is the output voltage V0. Output voltage V0 equal to 1 plus RF by RI into the voltage at V1. Okay. So how to find V1 here? V1 equal to, using the potential divider network, Vi into 1 by j omega C by R plus 1 by j omega C. Okay, I can find like this. So V1 equal to Vi into 1 by j omega C by R plus 1 by j omega C. Okay, simply substitute V1, replace V1 by this equation and simplify the equation. Okay, then we can find what is the output voltage at the higher frequencies. So now let us see the derivation part here. So here first V1, the voltage at V1, if I simplify this equation, so if I write V1 equal to Vi into 1 by j omega 2 pi f into C by R plus 1 by J 2 pi f into C. And if you do the LCM and do the cancellation, then numerator denominator J 2 pi fc gets cancelled and you will get V1 equal to VI by 1 plus J into 2 pi f into R into C. After that, we need to find what is a V0. V0 equal to 1 plus Rf by Ri into V1, where V1 equal to this equation. Just substitute in, replace this V1 by this equation. Okay. So if I replace V1 by this equation, then I will get V0 equal to 1 plus Rf by Ri into Vi by 1 plus J 2 pi f into Rc, where this parameter is nothing but the gain value A. So that's why it has been replaced. And what are these Vi is there, that has been shifted to other side. So then we can get V0 by Vi equal to A. V0 by Vi equal to A by 1 plus J into 2 pi f into R into C. Okay. So I am replacing this parameter by A by 1 plus J into F by Fh I am replacing. So at the time, what is the Fh here? Fh equal to 1 by 2 pi R into C, where A equal to 1 plus Rf by Ra. This is the maximum passband gain of the corresponding filter. And what are this Fh is there? Fh is called as a higher cutoff frequency. Higher cutoff frequency. Now, if I find what is a modulus of, I need to draw the corresponding response graph. So that's why I will take modulus of V0 by Vi. Finally, V0 by Vi equal to modulus of V0 by Vi equal to A by square root of 1 plus F by Fh whole square. Like that I will get the equation. So this is the equation what I am getting here. Now, when the frequency value F value equal to 0, when the frequency F value equal to 0, at the time the gain value equal to simply A. So that's why when the frequency value is a low value, then at the time I am getting the gain value is a high value I am getting here. Now, as the frequency component is increasing and at the frequency F equal to Fh, what's happening here? The gain value I am getting is, if F equal to Fh, I will get A by root 2. A by root 2 is nothing but 0.707 times of A. Okay. So this frequency is called as a high frequency, higher cutoff frequency. So here at the frequency F equal to Fh here, the gain value is 0.707 times of A. So if I convert in the form of decibels, that is 3 decibels. From the maximum gain, the gain value is decreasing by the factor of 3 decibels, the gain value is decreasing. Okay. So now from this one, we can tell that. So here, when the frequency value is at F equal to Fh, the gain value is 0.70 times of maximum gain value. So the frequency of 0 to Fh is called as a pass band frequency. And beyond the frequency F greater than Fh, when the frequency F greater than Fh here, so the gain value decreases at the rate of the minus 20 decibels per decade, minus 20 dB per decade, the gain value is slowly decreasing. So here beyond this Fh, this is called as a stop band. Below this frequency Fh, this is called as a pass band. Okay. So this is the response of the corresponding low pass filter. Right? This is a gain expression, and where Fh equal to 1 by 2 pi Rc and the gain equal to A by square root of 1 plus F by Fh whole square. And what is the expression for A? A is nothing but 1 plus Rf by Ri. Okay. So this is a derivation part and this is the frequency response of the corresponding low pass filter. So now let us see the design steps of the corresponding low pass filter. If I asked you to design the corresponding low pass filter, at that time the first step here is choose some cutoff frequency. Suppose if the cutoff frequency is also not mentioned. Okay. So just I asked you the question as just to design a low pass filter, low pass active filter. Design a low pass active filter. That's only the question has been given. And I have not mentioned what is the cutoff frequency and everything. At the time, choose the value for first step is choose the higher cutoff frequency. With respect to low pass filter, the frequency is higher cutoff frequency Fh. At that time, the next step is choose the capacitance value is less than or equal to 1 microfarad. Okay. So after that, you have already assumed Fh value and you have taken one C value. Now what is the unknown parameter? you need to calculate what is the resistance value R. So from this equation, R equal to what will happen? R equal to 1 by 2 pi FH into C. So simply find what is the resistance value of the R value. Okay. So next, after that, you need to find the gain. Gain is required because in your circuit of the low pass filter, RI is there, RF is there. Okay, so that's why I need to find the gain value. Suppose if I imagine, just assume some gain value, A value. A value take it as a 10, 1, 4, anything take it. So based on that, suppose if I consider the gain value A equal to 2. If I take gain value A equal to 2, 1 plus RF by RI. So if I take this time, then RF by RI equal to simply 1, which is of equal to RF equal to RI. So whatever the RI value you are taking, same RF value you need to consider. Okay, like that, whatever the gain you want, assume it. Suppose in the question itself it has been given, then it's good. Whatever the question given, based on that to do it. Okay, so now this is the steps. What is the first step? If the frequency nothing has been given, first choose the higher cutoff frequency. Later choose the capacitance value. Based on the frequency and the capacitance, calculate what is the resistance value you are getting. Now based on, choose some passband gain value. Now based on the gain value, see what is the value of the RA value as well as the RF value. Okay, so this is the sequence of steps for the design of the low pass filter. Now let us see one problem. In this problem, design a low pass filter at a cutoff frequency. Cutoff frequency is given. Cutoff frequency given is a FH has been given. FH equal to 2 kilohertz is given. Okay, and the passband gain A equal to 2 has been given. Okay, what is the first step I need to do? The first step I need to do is now assume what is the capacitance value. If I assume the capacitance value, now first I am taking the, what is the given parameters, I am taking like this, FH equal to 2 kilohertz and A equal to 2. Later assume some capacitance value. Here I am choosing the capacitance value equal to 0.01 microfarad I am choosing here. Based on that, use the expression FH equal to 1 by 2 pi RC and you require only the resistance parameter R is required. So calculate what is the R value, resistance value, calculate from this expression. So I am getting the equation is 7.95 kilo ohms is the resistance value I am getting here. Now the passband gain is given. Passband gain A value is given means find 1 plus RF by RI equal to 2. Now based on this, calculate what is the RF value. So here simply RF equal to RI. So assume some 10 kilo ohm, 1 kilo ohm, like that. Assume some any of the value you can assume. Okay, this is the way. This is the design steps and this is the way how to solve the problem with respect to low pass filter. Okay, I think today we have covered the introduction of the corresponding active filters and the passive filters, and we have seen the first order low pass filter we have seen, and what are the design steps, okay, and what is the derivation we have done, and at the same time we have seen one problem also we have seen. Okay, let us meet in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.